Welcome to lecture 3.3 of the course on time frequency analysis and wavelet transforms. In this module, we are going to learn particularly the discrete time Fourier series. In the previous two modules of this unit, we had looked at continuous time periodic and aperiodic signals. Now, it is time to move on to the discrete time case. So, we are slowly tending to practicality because in practice we are going to deal with sample data. So, the discrete time Fourier series is concerned with discrete time periodic signals, as you must have guessed, because we had continuous time Fourier series for continuous time periodic signals. And naturally, now we are going to talk of power spectrum, because recall the analogy for the continuous time case. So, the energy spectral density vanishes that we had in lecture 3.2, and now power spectrum comes back. And we will also study a connection between the power spectrum and the autocovariance function. It slowly leads us to the properties of the Fourier transforms that we will study in the next module. Before we go further, it is very important to understand the consequences of moving from the continuous time case to the discrete time case. And for this, recall the concepts that we learned earlier in unit 2, where we talked about the case of discrete time signals, and we particularly noted that discrete time sinusoids are unique only in a fundamental interval, which is of width 1 in cyclic frequency. This interval could be minus 0.5, 0.5 or 1, 0, or if you look at angular frequency, it is actually minus pi to pi and so on. Now, the consequence of this property of discrete time sinusoids, why are we talking about sinusoids? Because the basis functions or the building blocks in Fourier analysis are complex sine waves. In the continuous time periodic case, we considered complex sine waves of all frequencies. Now, there is no point in considering complex sinusoids of well, when we say all frequencies, harmonics, but from minus infinity to infinity. Now, the idea in discrete time Fourier series is going to be the same. I am going to express a discrete time periodic signal as a weighted combination of discrete time complex exponentials, but with a prime difference being that now I am not going to consider harmonics from minus infinity to infinity, but I will restrict myself to this fundamental interval, because outside this interval the basis functions will have aliases in the fundamental range. So, there is no point in really including them, or we can say that they have been already included. Either way of you can look at it. And of course, something to recall that the period of a discrete time signal can only be expressed in samples rather than in time units. Now, this is the point that I just mentioned. A discrete time signal of fundamental period n can consist of how many frequency components? N frequency components. What are those frequencies? Now, these are 1 over n, 2 over n, up to n minus 1 over n, besides the usual DC component that we have. Notice that we now switch to lowercase for the frequency, lowercase notation, because now we are dealing with discrete time signals. So, the main message is the Fourier representation of the discrete time periodic signal will not include infinite harmonics, but only a finite number of harmonics. That makes life easier, of course, in many ways. And as I mentioned early on, we are dealing with periodic signals, so we are going to talk about power and power spectrum, but not power spectral density, because I am only looking at a discrete set of frequencies. So, just to now put things in perspective, I have the discrete time Fourier series in this top row, which is the focus of the discussion in this module. Here you have the synthesis equation. As I mentioned earlier, you have a finite summation, unlike what we had in the continuous time Fourier series case. The index that keeps track of frequencies is this small n, which runs from 0 to capital N minus 1. As the index runs from 0 to n minus 1, I am actually spanning the entire fundamental frequency range from minus 0.5 to 0.5 or 0 to 1, whichever way you look at it in cyclic frequency. And this is the usual Fourier analysis equation, or the expression for the Fourier coefficient. And on the right hand side, you have the power spectral decomposition result, once again due to Parseval, which tells me how the power is being decomposed in the frequency domain. And once again, I have mod Cn square representing the quantifying the contribution of the nth harmonic, which is the discrete time exponential to the overall power of the signal. All right. Of course, the bottom row has the discrete time Fourier transform, which is a subject of discussion in the next module. Okay, so we already have had introduction on why we had the summation running only from over the finite length of n and so on. So let us look at this Fourier analysis equation and the synthesis equation a bit more in detail. First point, again to reiterate, the family of basis functions that I am going to consider is now finite. This is the family of basis functions e to the j 2 pi k n over n. This big N now is a period, it is not the number of samples that you have and so on, all right. And here n, that is, it should not read k here, actually n runs from 0 to n minus 1, and the Fourier series of course is expressed this way, while the Fourier coefficients are given by this expression as you have seen in the table earlier. One thing that you can notice is the similarity between the expressions for the synthesis and analysis equations. They look very alike except for the dummy indices being different, and two other differences. You have a factor of 1 over n in front of the summation for Cn, and the second difference being e to the j is being replaced by its complex conjugate, all right. So that gives me a nice advantage when I am computing the Fourier coefficients or recovering the signal. I need to just write one piece of code, all I have to do is have this factor 1 over n, or in many and just switch the sign of j. In many textbooks you will see in place of 1 over n you would have 1 over root n in the Fourier series expansion and a 1 over root n here, so that the similarity is much more strong, and it on a lighter note it helps us in memorizing the analysis and synthesis equations in a easy manner. Okay. So moving on to the power spectrum, the power spectral decomposition, we have already seen this result in the table that I showed you earlier. The main message here is that mod Cn square quantifies the contribution of the nth harmonic to the overall power of the signal, and n again runs from 0 to capital N minus 1. And the difference again between the results in the continuous time and discrete time case is only in the restriction in the number of frequencies, otherwise all the interpretations carry forward. So there is not much to discuss as far as the interpretation of Cn is concerned. Now a few interesting properties on these Fourier coefficients. Firstly, the Fourier coefficients enjoy the conjugate symmetry property, that is C subscript n is C star, the complex conjugate of subscript big N minus small n minus 1, and this is true only when you are looking at indices apart from 0 and n by 2, assuming n is even. And very importantly, the Fourier coefficients are periodic with the same period as the signal, all right, which means the power spectrum in fact repeats itself. That again is a consequence of this aliasing property of the discrete time exponentials. All right. So the power spectrum also enjoys the same periodicity property as the signal. So let us walk through an example to understand the workings of the discrete time Fourier series. I have just taken a periodic signal and I am giving you the values of this periodic signal over a single period. As you can see, the period is 4, and all I do is to compute the Fourier coefficients. I invoke the expression that I have seen earlier, plug in the values of x of k and work through the math, it gives me this expression. And if I evaluate the coefficients at all values of n, small n, 0, 1, 2 and 3, then I obtain C0 as 1 over 2, that is the average of the signal. You should check. Always the coefficient for frequency 0 is the mean of the signal because of the expression itself. So plug in n equals 0 here, you would obtain 1 over n sigma xk, which is nothing but the sample mean or mean of the signal. And that is a quick check for your calculations. Then you have C1 and C2 and C3. Notice that C1 and C3 are complex conjugates of each other by virtue of the property that we discussed here. And this property does not apply to C0 and C2. Okay. So, that is something as a quick verification. I will conclude this module with a very important result, which when extended to the class of random signals leads to what is known as a Wiener-Khinchin theorem. This result says that the power spectrum of a discrete time periodic signal and its autocovariance function, remember we defined the autocovariance function for discrete time periodic signals early on in unit 2, they form a Fourier pair. What it means is the power spectrum is the Fourier transform or the discrete time, you can say not transform, but it is a Fourier coefficient of the Fourier series representation of the autocovariance function. So, this is the autocovariance function is a function of lag L. This is the Fourier representation for it, that is in 7b, and in 7a I am calculating the power spectrum as a Fourier coefficient of this representation, all right. And this result is fairly easy to prove. So, I will actually leave it to you to verify if this holds. Of course, you should remember or recall the definition of the autocovariance function for a discrete time periodic signal that we had in lecture 2.1. So, plug in this expression for the autocovariance function into equation 7a and show that it is the same as what we have here in equation 4, that is Pxx of n you should get as mod Cn square. In fact, as a quick numerical check, just set n equals 2 without assuming any values for x and you will be able to verify the result. Now, why is this result so important? For two different reasons. One, to compute the power spectrum, I need not go through the Fourier transform of the signal. I can first compute the autocovariance function and then compute the Fourier transform of the autocovariance function. Then you may ask, well, so what, right? The point is when I move to the class of random signals, although we do not do that in this course, Fourier transforms or Fourier representations of random signals do not exist, but autocovariance functions can be defined for random signals. So, what I do is I define power spectrum not via the Fourier transform of those random signals, but as the Fourier transform of the autocovariance function. Remember, when I take the Fourier transform of the signal, I have to evaluate the squared magnitude. In this case, it is a periodic signal, so I am going to compute the Fourier coefficient. After computing the Fourier coefficient, I have to take the squared magnitude. In this case, I compute the autocovariance function, and the moment I take the Fourier transform of the autocovariance function, I get the power spectrum. This result will also be visible to us in the case of discrete time aperiodic signals and is used widely in calculating the autocovariance function. In fact, the XCORR routine in MATLAB uses this result. It actually computes the Fourier transform and then of the given sequence and then constructs the power spectrum and then evaluates the inverse Fourier transform to get the autocovariance function because it is computationally more efficient. Okay. So, with this note we will come to a close for this module. It is a fairly short one. In the next module we are going to discuss discrete time Fourier transforms, which will take us a bit more closer to reality, because in reality I am not going to have discrete time periodic signals, I am going to have discrete time aperiodic signals more often, and therefore I should know how to deal with them and eventually end up with discrete Fourier transform, which is the most practically relevant version of the Fourier transform to us. So, these are a couple of references for your perusal. Of course, there are plenty of other wonderful references. Thank you.